In this part of the video, we're going to review the domain of a function, the values of x on which the function is defined, and we're going to use two different notations to do that. We're going to use an interval notation and a set notation. Okay, so here we go. The domain. Again, this should be a review for you. The notation may or may not be a review. Alright, so what are the allowable values of x? Certainly x cannot equal 2. The function is not defined at x equals 2. The function cannot equal 7, so on and so forth. The function can't equal 5 because of the open circle. The function cannot equal 1, open circle. The function can equal negative 100 because this arrow tells us it keeps going on forever. So all values of x to the left of this arrow will be included in our domain. So x is an element. Now check out this notation you might not be familiar with. It's a C, but then when I put a slash on it, it makes an E looking figure, and it means the element of, or x belongs to. Now in this interval notation, I'm going to use a combination of parentheses and brackets. A parenthesis is used when it cannot include the number or character. So left to right, it can go all the way to negative infinity, but I always use a parenthesis around infinity or negative infinity because they are not real numbers. In fact, they are just concepts. So the leftmost x value can be negative infinity all the way up to the value of 1, but it can't equal 1 because of the open circle. So I will use a parenthesis. And then there's a gap, and I use this union symbol to show us the collection of these two different intervals. The second interval includes a 3, so I will use a bracket, and it goes all the way up to 5, and I will use a parenthesis because it can't equal the 5. So that is our collection of x values on which the function is defined using interval notation. And now for the set notation, I'm going to say that we have a set of x values, another Greek symbol, which is the slash, which means such that. So it's a set of x values such that, and the way I'll write the interval here is from negative infinity is less than x, which is less than 1. So x is between negative infinity and 1. Notice there are no equal signs. And then instead of the union symbol here, we'll use an or. 3 is less than or equal to x, which is less than 5. So set of x such that it has these inequalities. Example 2, the domain is going to be this x is an element of a particular interval. We're going to go from negative 5 to 2, not including the 2, in union with, not including the 3, all the way up to 6, but including the 6. And for the set notation, it's going to be the set of all x such that negative 5 is less than or equal to x, which is less than 2, that interval or inequality, together with, so or, x is between 3 and 6, not including 3, but including the 6. In example 3, looks like what we have, what we call an asymptote here, an imaginary vertical line that the function does not pass through, or to say it differently, a value of x for which the function is not defined. Let's write the domain. So, what are we going to say here? X is an element of, well, we'll go from negative infinity all the way up to negative 3, not including the negative 3, in union with the negative 3, picks up on the other side of it, all the way to positive 3, and then stops. And then we are going to do the union with, and we have these singular dots here, and the only x value represented there is a 5. It includes the 5, and it also includes the 7. A little clunky, but that is the interval notation. Now for the set notation, we are going to say the set of all x such that negative infinity less than x is less than negative 3, or negative 3 is less than x, less than or equal to 3, or, now for these singletons, we'll say x equals 5, comma 7. So x equals 5 or x equals 7. And there's our set. In example number 4, we do have an open circle, but it looks like that x value is still represented because this dot allows the function to be defined at 2. So our domain now is going to be x is an element of negative infinity to infinity. In other words, x can be any real number. There are a couple ways we can write that. We can say that x is an element of the reals. That's an R with a funny looking back to it. That's a recognized way to say x can be any real number. Another way you can do it is simply to say that x can be any real number. For the set notation, we can write the inequality as such. You will also see it written like this: that x is an element of the reals. This is sort of a hybrid of set and interval notation. It is also sometimes written as simply a set of all reals. So that is also permissible. And also we can say a set of all real numbers. So there are a variety of ways to write it when x can be any real number. In this particular graph function, the only thing that x cannot be is the number 1 because we have open circles here and here. So let's look at some of the ways we can write that. We can say that x is an element of, this is a little bit longer but acceptable. We go from negative infinity to 1 and union with 1 to infinity. So when there are just a couple values that it can't equal, it sometimes suffices to just say what x cannot equal. So x cannot equal 1 counts as the interval notation here. For the set notation, we can say x such that negative infinity is less than x is less than 1, or 1 is less than x is less than infinity. Or we can say x such that x is not equal to 1. In this last example, you can see that we have an asymptote here, an asymptote somewhere out here, asymptote here, and it looks like this pattern is going to keep on going and continuing. You might recognize this function as the cosecant of x. This one, there are an infinite many of intervals, so I cannot write it with a bunch of unions. What I have to do in this case is I have to express the domain with the values of x that it cannot equal. I have to do that here. So x cannot equal, well, do you know the cosecant function? Do you know the pattern? This is going to be at x equals 0. This is going to be at x equals pi, and then 2 pi, x equals negative pi, negative 2 pi. Do you know how we'll express that? Well, let's see. Pi times k, where k is an integer. Those are the values that x cannot equal. Same deal with the set, x such that x cannot equal pi times k, where k is an integer.